Hello and namaste. My name is Brandon, and welcome to the next video in my series on basic statistics. In this video, we will continue our playlist on variable transformations, looking specifically at the square root transformation. So let's get started. So the square root transformation is good for low to moderate skewness. So if the data is severely skewed, we might use something more powerful like the log transform or the multiplicative inverse transform. So values cannot be negative. This should make sense. We cannot take the square root of a negative value. Oftentimes a constant is added, so the smallest value is 1, and we will do that in this video. For example, if the smallest value is -4 in our original data, then the first step would be to add 5 to each value before applying the transformation, and the reflection for that matter. So our goal in general, in most cases, is to get the smallest value of our transformed variable to 1. Now, if the variable is left skewed, so a long left tail, then the variable is also reflected to be right skewed, and we covered why that is in previous videos. The process might be a shift to a minimum of 1, then reflect, then transform. Shift, reflect, transform. Now, we must keep track of all changes from the original data. It's very easy once we do a bunch of transformations to variables to get lost of what we've done to them. And then when we go to interpret the outcome, we have variables that we don't really remember what we did. So it's really important to name our variables in certain ways, which I'll show you in Excel, or to at least keep track in some way so we can reverse the transformation to do predictions or whatever else we might need to do at the very end, like communicate it to stakeholders. So remember, we have skewness direction, right skew, left skew. Right skew means a long right tail, and left skew means a long left tail. There's also magnitude of skewness, so mild, moderate, severe, and then the same could be true for left skewed, and that will help us determine maybe what transformation is appropriate for the shape of the data we're starting with. So here's some toy data to show you what's actually going on in this square root transformation. So here I made up some data. We have 11 observations. Our start data is just 0, 10, 20, 30, 40, evenly spaced up to 100. Then we took the square root of those original numbers, which we have there in the second column. And then what I did is just for scaling purposes to get back to the start data scale is just multiplied each one of those by 10. In and of itself, this is a variable transformation, but we're just doing this for teaching purposes. So start data, some toy data, square root, times 10 to get it to the same scale as the original. Now, if we did a generic plot of our start data, we would just have 11 observations that are evenly spaced. So they're all 10 apart. We can see those dots are evenly spaced. Now what happens if we graph those dots on the transformed, the square root scale? It looks like this. So what happened? Well, we can see that there is an expansion in the lower values, and then there is a compression in the higher values. So the square root transform expands the lower values apart and then compresses the higher values. The result is that it takes a skewed data set and then shifts it to the right and compresses those higher values to make the distribution look more normal. Now on a graph, it might look like this. So here's our start data in blue. That's just the simple 0, 10, 20, 30, so on and so forth. And then the red line is a graph of the square root transformed values. So what do you see here? Well, we have the expansion of smaller values here in this region, and then the compression of the larger values up in this region here. So this is another way to graphically represent what's actually being done numerically to those values when we do the square root transformation. Expansion on the low end, compression on the high end. Now, compression slope. So if we were to graph just the square root of x, remember it looks like this. So it starts at the origin and then it increases pretty rapidly, but then it levels off as the numbers get higher. This is another graphical representation of what happens in a square root transformation. So a side note here. The function we're looking at is the square root of x. If we took the derivative of that function, and don't freak out, if you've not had calculus or don't remember calculus, if you've had it, you don't need to. I'm going to walk you through everything here. So the derivative of a square root function is 1 divided by 2 times the square root of x. Easiest way to get there is just using the power rule. So the first derivative is the slope of that tangent line there. So if we went ahead and put the value of 1 into that derivative function, we would get a value of 0.5. And we can see that that is the slope of that orange dotted line over there on the left. Now, what if we put 4 into that function? Well, now the slope is 0.25. It's getting flatter. How about at 9? Now it's 0.16, flatter still. So we can see the compressive nature of the square root transform by looking at how the slope of the derivative of that function changes over time. So expansion and compression over there on the high end. For those of you who are interested in how we got this derivative function using the power rule, I will talk about it very quickly. Our original function is square root of x. We can also write that as x to the 1/2 power. Now using the power rule, the exponent rule, in calculus or pre-calc, wherever you learned it, first thing we do is we drop the exponent value down in front. So it's 1/2 square root of x, or 1/2 x to the 1/2 power. But we first have to subtract 1 from the exponent. So we end up with 1/2 times x, that is to the negative 1/2 power now. See how that works? We drop the 1/2 in front, subtract 1 from our original exponent of 1/2. Now we have 1/2 x to the negative 1/2 power. Now, knowing our rules of algebra, we know that if we have a negative exponent, we can just drop it down to the denominator in this fraction here. So now we have essentially 1/2, but because the exponent of x was negative, it's now in the bottom. We could look at this as 1/2 times x to the 1/2 power, and we move that to the denominator because it's negative. That's how we derive that derivative there. So that's a side note for those who wanted to know. If you weren't interested, I am very sorry for wasting your time, but I know there are a lot of people that would want to know how we got that and then inserted these numbers to the tangent slope of that derivative function. So remember, we're using the Boston data set. We've already covered that in previous videos. We have all these variables, and we're trying to predict or model the median value of the home based on these other variables. So what we're going to do is hop into Excel and actually do this in Excel. We're going to reflect the PT ratio variable because it is left skewed. We're going to make it right skewed. And then we're going to do a square root transformation of that variable. So the original, reflect, and mild transform to make it a bit more normal. And then we will numerically see how much or if it makes any difference in the relationship to our target variable, which is median home price. Let's hop into Excel and do that, and then we'll come back. So here we have the Boston dataset in Excel. The first several columns, A through M, are our independent variables, and then the column N, median value of the home, is our target or our dependent variable. Now what we're going to do here is see if transforming the PT ratio variable will get us a better relationship with our dependent variable or our target variable through some transformations, and do some trial and error to see if the transformation is worth it or not. First thing to note here is that I have given this table a name. So this entire table of data has a name. If I go to the name manager, which is in formulas, name manager, you'll see here this top one, Boston, is this tab and this set here. The one you download from my website might be a bit different, but it is named Boston in that one as well. So we can refer to all of our columns and things like that just using Boston, which is really nice. So the first thing we want to do is some introductory analysis of this PT ratio variable to see whether or not it is a good candidate for transformation. So the first thing we can do is just kind of find the min and max. So I can do min and max. We'll delete these here in a second. This is just some introductory stuff. So I can do equals Boston bracket PT ratio. And then for this one, I want to have the minimum. So I can put that inside of a minimum. And so the minimum is 12.6. So the maximum will be, I think it's 22, but Boston bracket PT ratio close bracket. And the max is 22. So our minimum is 12.6 and our maximum is 22. Just a reminder that PT ratio stands for pupil-teacher ratio. So the high value here is 22, so 22 students per teacher, and then 12.6 students per teacher. Of course, we can't have a 0.6 student, well, hopefully not. So again, these are just values that have been aggregated, so we can use them as is. So everything looks good here. Now the first thing we want to keep in mind is that if we're going to do a square root transformation, we can't have any value less than 0, so we seem to be in good shape here. I'm going to go ahead and delete those. Okay, now the first thing we want to do in our transform is see if we should reflect it. So the easiest way to do that is I'm going to select that entire variable, that column. I don't even have to actually make this. I'm going to go to Insert, Charts. I'm going to go to All Charts and Histogram. And then here I can just see it visually. So here I can see just by hovering over it that this is left skewed. So we have a long tail to the left in this graph here. Now remember, we want things to be all right skewed if they are skewed. So that means we're going to do a reflection first. Now, in terms of severity, this seems like a relatively mild skew. So we can use the square root transform on this and see how it works. So 2 steps: reflect because it's left skewed, and then the square root transform because the skew is relatively mild. So go ahead and click cancel, and we know what to do. So the first thing I'm going to do is go back up to the top and create a new column. So insert column. I'm going to name this PT ratio underscore R for reflected underscore square root SQRT for square root transform. That way I know exactly what I've done to this transformed variable. So the first thing we're going to do is the reflection. Now remember, we talked about reflections in previous videos. What we're going to do is find the maximum of the PT ratio variable, then subtract each value from the maximum, and then add 1. That will be our reflection. So let's do that first, then we'll do the square root after that. So equals the maximum, and I like to build my parentheses as I go, and you'll see why in a second. So max Boston PT ratio, so bracket PT ratio right there. Now, just for education's sake, I'm going to go ahead and close this and show you what it gives us. So remember we said that the maximum was 22. We can confirm that we've typed in our formula right here by just hitting enter, and it gives us 22 back. So we know we're on the right track. Now, what we want to do here is subtract each value individually that's in the original PT ratio. So we're going to go ahead and go to the end, minus the value here, okay, and then hit enter. So now things should be flipped. If you notice here, this high value of 21 now has a value of 1. If we scroll down and find our original maximum of 22, so here we have 2 maximum values that are now 0. Technically, we could leave this like this because 0, we can take the square root of 0, just 0, no problem there. Now, like I mentioned in previous videos, we like to have the minimum value as 1 instead of 0 because it tends to make things a little bit neater, especially when we use other transformations where the minimum value has to be 1 or greater. In theory, we could leave this as is because our minimum is 0, which is fine. Now, to change that 0, that's the minimum now, reflected to a 1, we're just going to add 1 to what we've calculated here. So I'm going to go ahead and put all of this in parentheses, and then just add 1, and there we go. So now, if I scroll back down, I should have kept track of where those were. We should have 1s. There we go. So the 22, which was the original max, is now a transformed minimum of 1. That's how we can tell that our transformation or reflection worked. Now what we can do is go to this again, do the same thing. Select that entire column, go back to recommended charts, histogram, which I think is here. This lets me hover. Now we can see that our graph is right skewed now. So instead of having the long tail to the left, our reflection has done what we wanted. It's made the skew to the right. That's exactly why we do reflections. Cancel out of there. Now, as we know, the next step we want to do is take the square root of that. So I'm going to go back up and wrap all of this just inside a square root. So SQRT, and then just Go ahead and put a parentheses there to make everything nice and tidy. Enter, and there we go. So now we have reflected the PT ratio variable, and now we have taken the square root. Now, if we look at a quick histogram here of this, it should look more normal. Recommended charts, all charts, histogram, and this. It has a little bit of skew to the right, but it is better than it was before. Now, we could have tried something more powerful, like the log or the multiplicative inverse, if we wanted to see if we can get this a bit more normal. But I think for our purposes, just taking the square root will be fine. Okay, so I'm gonna go ahead and click cancel out of there. Now, what we want to do is figure out if this made really any difference. So the way to do that is we're going to check the correlation between PT ratio, the original, and our target of median home value and our transformed PT ratio and median home value. So we'll go ahead and make a little column over here. We'll call this correlations. All right, so the first thing we want to do is grab our headers, PT ratio there, and then our PT ratio square root there. And now we want to have the target variable as well. So we know what we're correlating here. So what we're going to do is test those two correlations. So equals correlation, Boston, tab, bracket, PT ratio, close the bracket, comma, Boston, bracket, MED for median home value, bracket, close it, and there we go. So the correlation between the original PT ratio variable and the median home value was negative 0.51 approximately. Now this should make sense. So this should be a negative correlation because higher value homes should be correlated with lower ratios of students to teachers. Make sense? So if we have a school or district, whatever the measurement here is, with a low student teacher ratio, the homes in those areas tend to be higher value. And this exists today too. School districts and schools that have low student teacher ratios tend to be in districts with high home values, with wealthier people that live in them. Now, let's look at the correlation with our transform variable. So equals correlation, Boston, bracket. Now this time we want PT ratio with the transformed one, and then the target variable again. So median home value. Close. All right. So now it's gone up to 0.51. So we've had a bit of an increase in our correlation there. Now we can decide whether or not that's anything that's of value. Now we also notice that the correlation is positive. Why? We reflected the variable. So the correlation should be about the same, just the opposite sign, and that is indicative of the reflection we did in this variable. Now what I want to do is, just for the sake of seeing what would happen, let's also transform our target variable. So what I'm going to do here is insert a column. We're going to call this median value underscore SQRT. Now, as I mentioned in previous videos, sometimes this is just testing and trial and error and playing around and see what happens when we change some of these numbers. So all I'm going to do here is just take the square root of the median home value. Square root, Boston, bracket, median home value, close. And there we go. Typed that formula a bit wrong, but it fixed it for me. Thank you, Excel. Now we have the square root of our target variable here. Let's do the same thing. So these I can just copy down. But this, I want the square root, the transformed here. Just select those headers. There we go. I'll probably move this over so we can see easier. Sorry about that. All right, same thing. Equals correlation, Boston. Now we're going to do the same thing again. So PT ratio, the original PT ratio, comma, Boston. But this time we want the transformed target variable. So let's want the square root on it. Close. So now we're at 5.51265. And again, that is negative because we're using our original PT ratio. Now the same thing. So correlation, Boston, bracket, This time we want the transformed PT ratio and the transformed target variable. And close. So now we're at 0.5194. What we have done is do the transform, the original data was negative 0.508, somewhere around there. And then we got up to 0.51265 and then 0.5194. So there's some benefit there in transforming. There's not a whole lot of difference between these two. Obviously, the reflection changes the sign, but in terms of the magnitude, they're sort of about the same. Same thing up here. So we did gain a bit of strength in the relationship between these two variables by doing some transforms. Whether or not that makes enough difference in the overall model is to be determined. There's no hard, fast rule or anything like that to determine whether or not this is the best option. For example, we could stick with the original if we wanted. We could just do a reflection. So just doing a reflection at the beginning would make this positive. It would just be positive 0.50779, and we could stick with that. Or we could do something a bit different, a different transform if we wanted. So see how this works? Some of it is trial and error. What can happen if we're doing some big model here or some multivariate regression or something like that, if we can even squeeze out another 0.01 out of our correlation here, that can strengthen our overall model. Now remember, we didn't do anything to, quote, change the data. All we did was a mathematical transformation of these variables. And as long as we keep track of those transformations and we are consistent in using them throughout our model, and we repeat that with other variables through that process and over time, we can squeeze more prediction power out of our model by molding the data through transformations to better match the assumptions of the analysis technique that we are using. So we are back from Excel, and we could see, one, how to actually do the reflection and transformations if we wanted to, and then numerically how the correlation changed based on just doing some basic transformations. And it might not seem like 0.1 gain in the correlation between transformed variables is a whole lot, but in my experience, it is, especially when you do other transforms in multivariable situations, whether that is multiple regression or some other maybe machine learning model or whatever else you're doing. So whether or not the transformation is beneficial is really up to you and your analysis. My point here is just to show you how to determine if a transformation is appropriate, and if you're going to try one, how to go in and do it, at least manually, so you can see what you're doing and where the numbers are coming from. But in the end, it will really be up to you to try different things, run multiple models, and see whether or not these transforms are beneficial to the predictive power of your model, because you have brought these variables more in line with the assumptions underlying those techniques. And of course, we'll do the same thing for the log transform and the multiplicative inverse transform, and some others probably. So that wraps up this video on variable transformations, the square root transform. I hope you found this informational and it broadened the repertoire of your statistical and model building skills. And I look forward to seeing you again in the next video. Take care, my friends. Bye-bye.